Hello, everyone, and welcome to today's webinar. My name is Celeste Stroup, and I will be your moderator for today. Today's webinar is brought to you by the Critical Materials Innovation Hub, and we're excited for today's speaker, Tim O'Brien. Tim is coming to us from USGS, and he will be presenting on estimating mining project costs for modeling future mineral supplies. But before we dive into it, I want to go over a few logistics with you. So this webinar is brought to you by Colorado School of Mines and CMI Hub. This is we love taking future suggestions for webinars, so please feel free to email us at cmi@mines.edu, or in the exit survey that you will receive shortly following this webinar, you can share some suggestions there as well. This is a publicly recorded webinar and will be available on our YouTube channel in about a week's time. You can find us at Critical Materials Innovation Hub. Our recordings are also found at aimslab.gov/CMI. You can look at our previous recordings there. In this webinar, we encourage you to ask Tim, our presenter, some questions throughout the duration of his presentation. He'll be holding the questions to answer them at the end, but we do encourage you to ask them as they pop into your mind. You can put those into our chat box this week, and then we will look through those at the end. And with that, I would like to then introduce our speaker. So Tim O'Brien has an MS degree in geology from the University of Kentucky and University of Michigan, as well as a PhD studying tectonics from Stanford University. So lots of geology history here, and I'm really excited to learn from Tim. He's worked with the Department of Energy, the Department of Defense, all around some of these topics around critical materials and rare earths. So we're excited for your presentation, Tim. And with that, I will hand it to you, and we'll learn some more.
Let me unmute myself. One day I'll get it. So thank you very much for attending. And today I'm going to talk to you about some of the work that I've been doing over the last couple of years since working with the USGS, in which developing mining cost models so that we can, at the USGS, use it to estimate future supplies of various critical minerals or other mineral commodities. And so many people, they're going to be at this talk, are going to be familiar in that fact that mineral commodities are essential to the many technologies that we use today. Either that being lithium, nickel, manganese, and cobalt that goes into EV batteries for electric vehicles, or as well as the lithium that gets added to aluminum to make aluminum alloys stronger for lightweighting purposes. And then the always, hot topic, rare earths, which are important for rare earth permanent magnets, would go in within our EV motors, as well as wind turbines. And at the USGS, a report that we publish every year, which is the within the National Minerals Information Center, is the Minerals Commodities Summary. And within the mineral commodities summary, one of my favorite charts that always gets reported is this tornado chart seen over here on the left. And what this is recording the U.S. net import reliance of the 90 or so odd mineral commodities that we follow. And what I mean by net import reliance, in essence, that it is the percentage of our consumption that is derived from imports. What we see here is that, there are several commodities, 10 or so plus that have 100% net import reliance, and many more that have a greater than 50% net import reliance. And if you look at, the statistics of these over the last half century, what we see here, as you kind of go through the decades on this chart on the right, as they go from the, from the 50s, in which we have 21 commodities have a greater than 25% net import reliance, to in the 80s 46, and to eventually in around 2020, in which there are 59. But what's more reflective of this is not just the increase in the overall of the commodities that have a greater than 25%, but it's the many that have a greater than 50% to 100% net import reliance that it has been drastically increasing. And that can kind of reflect, two things. First, we're reliant on so much more variety of these materials. Back in the 50s, they probably were not looking at gallium, germanium that are crucial to the technologies we use today. But it also could be reflecting, kind of that decrease in industrialization, the loss of mining and processing that has happened throughout the years. And so it's not just important that we quantify this, import reliance, but we also want to know where these imports may be sourced from in the future. And in accordance with the Energy Act of 2020, the specific group I work for within the National Information Center is developing a supply and demand model for assessing non-fuel mineral commodities. And what's particularly important for today's talk is that what we'll be doing is estimating future supplies within 5, 10, and 15 years into the future. And well, we have a lot of information that maybe be able to obtain from these, kind of narrow timescales, the fives, where announced projects that may come out. But, what about these projects that are in the pipeline, that mining projects that, are 10, within this 10 to 15 year time frame? How are we going to know, or how are we going to have the information to assess which of these projects may be able to advance towards the production stage, and which one's going to be economically competitive? So really what we're going to need to determine which ones may be economically competitive so that we can, try to estimate the future potential mine production. What we're going to need are models that can estimate, the mine economics. And so, when I first started USGS, I was trying to do some work with modeling rare earth production in various using various scenarios. And my supervisor asked me, just being like, well, how are you going to, determine which project is going to go forward? How are you going to understand the costs? And just after kind of staring at him with, kind of two bright headlights, eyes that are headlights, and I'm kind of like, this is something I really need to look into. But so after kind of digging through the literature, I came across, luckily the fact that back in the 80s, early 90s, the U.S. Bureau of Mines did a lot of great work into this very aspect of determining mining costs, such as the two examples that I showed here. And so it's like, well, maybe we can integrate these models within the ones that we're trying to do so that we can determine which mines can be cost competitive. And so use this one over here on the left to continue on that work looking into rare earths. And what I did is took all the cost information from 25 or so mineral commodities, which you see on this chart to the right. And this is a one-to-one chart where we're looking at the reported total costs from those feasibility studies from those projects versus the calculated cost using this model by Thomas Camp. What we see here is that no matter the type of mineral processing flow that has been done, all these projects plot to the right of that one-to-one line, indicating that the reported costs for these projects are much higher than those obtained to the CAM, and so that these costs that were calculated were significantly undervalued. And so so this led me to the thing like, well, now we're going to have to figure something else out. But the fact that these models kind of were not we're not obtaining the costs that we see today, kind of makes sense for the sake that this one by CAM was primarily developed using information from precious and base metal mines just within the Western U.S. and isn't necessarily reflective of the kind of tech metals and the global distribution of the projects that we're going to be looking at. And so this led me to developing my own cost model for rare earths. And these are some of the regressions that came out as a result. And so I dug through all those feasibility studies again, took out all capacity data, and that is within the x-axis of each one of these, and then the cost information, which is in the y. Up in the top row, what we have is the capital costs or CapEx, and we have the three different kinds here: mine development, non-processing infrastructure, which is things such as roads, power lines, power plants, and then mineral processing infrastructure. And as we see here, as we increase in our mine capacity, or as well as the mill feed rate, and so therefore we're increasing in the size of our project, capital costs increase. And then also what we have is that a mine, underground mine is more expensive than an open pit mine. And we see is as we increase in the distance from some kind of town or existing infrastructure, the cost increases as well, signifying that the project is more likely more remote. So the more remote it is, the more roads that you have to build. And lastly, for capital costs, which here is the mineral processing infrastructure. So again, as you increase in that feed rate, the costs will increase, but also as well, as you increase in the steps, as you go from green for just beneficiation to red for beneficiation, cracking and leaching, to an ultimately producing a separated oxide, the costs increase as you increase in the number of steps. And for the bottom, what we have are the operating costs. And what we have here are, and each one is factored as modeled as a result of the mill feed rate. And similarly, for each one, as you increase the feed rate, the costs decrease over that increased feed rate, indicating that we have our efficiencies of scale, so becoming more optimal. As well, the underground costs of mining are more expensive than the open pit. And then similarly to the mineral processing, infrastructure here, as you increase in the number of steps from, going from producing, doing that acid cracking and leaching to separated oxides, the costs are more expensive. And so, if you add all those regressions together, what you can obtain the cost of that project. And if you want to do it for several projects, you can generate a cost curve. But if we really want to, assess, what kind of projects may be, able to produce, rare earths into the future, we kind of need to take that 2-ton gorilla, in the room, in the fact that China is the dominant rare earth producer. And so on these charts on the left is I've modeled 16 unknown mines, 4 from China, which are those in the red boxes, and then 12 from the rest of the world. And then one of the reasons, China is the dominant producer because it is able to produce rare earths at a much cheaper rate than the rest of the world. And so to see how cost competitive these operations are in comparison to China, what I did is model these operations in China using an 80% reduction in labor costs, as well as a 20% reduction in power costs. And one of the projects that were included is the Bayan Obo, which is an iron oxide mine, which produces rare earths as a byproduct of that iron ore. And so, only costs related to pertaining to the rare earths were included. And to assess which projects could advance towards the production stage, what we did is put the costs within the net present value equation seen on the top here. And for this, we used 4 different price ranges, and those prices were held constant over the life of the mine. So, and if a project had a net present value of greater than 0, that project was able to advance. And then if it was less than 0, it was not. And so over here on the right is the result of those calculations. And what we see is that, what we have here is the potential rare total supply of the rare earths that may be produced if those projects were able to advance. And this is for each of the magnet rare earths. And so after export restrictions, after China initiated export restrictions in 2010, prices skyrocketed in 2011. And so see the result using the 2011 prices, essentially almost all the projects were able to advance and produce. So only 4 did not yield positive net present values. And then in 2016, in 2016, those export restrictions were uplifted and they were removed, and then the prices crashed. And so as a result, the only 2 projects were able to yield positive net present values, and both of them were from China. And so, and lastly, if we kind of use, present day and the not too distant future prices, what we have are 5 mines yielded positive net present values, 3 from China and 2 from the rest of the world, the Mont Vale in Quebec, Canada, and the Zansko Drift in South Africa. And so if you were to include the production from those 2 projects into the total supply of rare earths, what you would get is around 11% dysprosium, greater than 9% terbium and neodymium, and as well as around 8% praseodymium that would contribute to the global supply of rare earth oxides. And so what we see here is that just from just knowledge of a couple simple mining parameters, what we can do is estimate future supplies within rare earths and see which projects may have a potential to be economically cost competitive. But we needed to do this for many commodities, not just for rare earths. So it was really, if I was going to go through all these feasibility studies for, gold, copper, silver, and everything like that, this was just going to take way too long. And so what I needed to do is think of some way in which we can take that kind of similar idea of using just simple mining parameters to estimate these costs, but do it within, just determining one equation. And so this was not going to be done by doing a simple univariate regression model. That's been shown, and those are, the statistics on those are not great. So what I thought was to do is apply some multivariate regression, which takes the effects of several variables into the relation of that project cost. Try to go through this quick. And these are the various exploratory variables that were considered for the regression analysis. And so data was obtained from S&P Capital, and what we got is around 29,000 projects or operations. We looked at things such as, not just what kind of commodity it is, but also, what type of mine is it? Is it an open pit? Is it underground? Or how many mines? There may be 2 open pits on the same project. And then what kind of processing methods and what kind of forms were they going to produce? And then as well as that, looking at some numeric variables, and the ones that are highlighted in red, those are the ones that were specifically chosen for the regression analyses. And so if you have any questions, how these variables are chosen and any other methods related questions that may not get addressed at the end, please go to the paper that I've referenced here at the bottom to get some more information. But these numeric variables that we looked at are things such as, life of mine, the feed rate, as well as the resource reserve tonnage and grade. And for cost information, we were able to get cost info, OPEX and CAPEX for 28 mineral commodities. And each one of these are down here. And this came out to be from a roughly 1,500 mining projects. The costs were adjusted for individual countries' inflation rate for the timing of which that data point was reported. And so over here on the right is on the top we have some statistics of just the counting statistics for the various costs that we have for each commodity. And the number reported at the top of each of the bars is the number that we're able to obtain, the number of data points we were able to obtain. And really the kind of striking thing that stands out is that there's really this uneven distribution of the data, in which a lot of the data is really encompassed within copper, gold for the most part, but then also some silver as well as zinc operations. And so to kind of deal with this uneven distribution of the data, what I did is develop 2 separate methods here, is that looking at for cost-specific regressions as well as non-commodity specific regressions. And so for the commodity-specific regressions, we were able to further break down those costs into the number of mines, and then also the mine types that were included. So we're only for this study primarily concerned with open pit and underground mines. And in addition to just into the mining type, we're also looking at the extractive metallurgy. And if we have any hydro or pyrometallurgists on this call, you know that there's many different types of, numerous different kinds of processing flow sheets. And so to account for that, really, I aggregated everything into four, broad categories where you go in from basic, which does, ore washing, beneficiation, or heap leach, to advanced, which is doing, some kind of refining to a highly pure metal. And then for the non-commodity specific regressions, the goal of this was to take those commodities that had minimal amounts of data and combine them with the commodities that have large amounts of data. So somehow figure out a way to combine, a gold project with a platinum project or a palladium project, which didn't have as much information obtained. And this was to be done by, combining those which have similar properties. And that was done three ways. Either looking at the ore deposit type, the mine and processing type, and then a clustering analysis. And again, if anyone has any more information about, wants any more information about that, please see the methods section in the paper. So all in told, I think about a little over 400 different equations were produced. And so in which, each one could be, be utilized and put into whatever, model that you are developing as well. But also one of my colleagues and co-authors, John Ryder, put together a really great dashboard and where you can model individual projects. And where you can, by filling in some of the inputs and varying them up on the left, what it will do is automatically adjust the costs that we see here as well as the net present value of that project, and it'll give you it'll give you an updated discount flow. That will be adjusted. Again, then see here for, it's included within the supplementary information. Kind of the last part of that project is what I've kind of referred to as the menu. For those non-processing, non-commodity regressions, you really don't know, just by filling it in which type of method that you should choose. And so by putting this kind of menu or chart together, which shows the errors, in which I've been shown as the percent difference between the reported and the estimated cost, it will indicate those with the lowest difference, percent difference between, the lowest errors and the smallest number should indicate which type of regression that you should, might be the most appropriate for you to choose. All right, so we're going to go through some case studies here in which how, possible ways that the model can be applied. So the first thing we're going to look at is copper. And, many people, they're going to be, familiar with the copper market, and know that there is, with the energy transition as well as the increased demand in data centers, there's been a significant increase in demand in within the copper production. And so one of the scenarios for demand is that by IEA, which is suggested anywhere between 33 to 38 million metric tons of copper by 2040. And if we look at this chart on the left by the IEA, what we see here from these are the bars are the expected production from announced projects, and this is the various demand scenarios. And what we see by 2040, there's going to be a significant gap, which equates to about 10 million metric tons. So what I wanted to see is, are there enough projects in the pipeline to meet these IEA demand scenarios? Those that have not announced, those projects that have not announced that they, what their productions may be. And so can they fill this gap? And then also there's been a lot of, news about, if, with these high demands, we're going to need to raise the cost of copper so that these projects have the economic competitiveness and the potential to advance towards the production stage. And some people are calling for as high as $20,000 per metric ton of copper. So I wanted to see is it feasible for these projects to do it with just the 2023 metal prices? And so what I did is go back to S&P and look at projects that fell between kind of reserves development, those that have kind of they're getting ready to say what their resource is, to all those that have looked at and have completed a feasibility study. And from that, you got about 710 projects within the pipeline. And I bracketed between these development stages because those are the types of projects that would not have announced, but also maybe able to come online by 2040, due to the lag, the long timelines that it takes to advance a project towards production. I included both primary projects that will produce primary copper, as well as projects that will include copper as a byproduct, either that being a gold mine or nickel mine that's going to co-produce copper. I used those 2023 prices. So, for example, copper was about $8,500 per metric ton at the time, and fed them into the net present value equation again. And so as a result, and again, similar, if a project was above zero, it was able to advance. And from the 710, 395 projects yielded positive net present values. And so if you add up the amount of copper that come out as a byproduct with those that are produced as secondary and then primary copper, what you have here is going to be the summation of all that. And what it does is just barely meets that 2040 IEA scenario. So we have 10 million metric tons of copper. Yes, and that is using that 2023 price. And yeah, if you use that $20,000 per metric ton copper, yeah, you do get some better, we do get higher production, but that does not necessarily mean that we have to have it to be able to meet these demand scenarios. And so now let's see a copper case study 2. And so often not talked about mineral commodity is that it's platinum, and that it's really important for reducing greenhouse gas emissions. There are crucial components within catalytic converters. So within your in your car, so people were stealing them, from time to time, and then as well as their use within fuel cells and hydrogen generation. The interesting thing for supplying of platinum is that they're primarily obtained from within 5 countries. And if we look at this chart on the bottom right by the CPM group, what we see here is that roughly 2/3 of the potential supply is derived from South Africa. And so, it's like there is nothing to say that there is, we don't foresee any kind of potential problems of not obtaining our platinum supply from South Africa in the not too distant future. But that does put the global market at risk when you have too much reliance of production from just one country. And so what we want to see is there a way that we could expand or diversify our supply of platinum from just one country? And so, although that platinum is it's dominated within in South Africa, platinum group deposits are just distributed widely globally, and they're primarily found within like these really ancient cratons within South Africa or within northern North America. But there's this phrase that gets used in mining, and that is the grade is king. And the fact that South Africa hosts some of the highest grade operations and projects within the world. And so what we have here on the right is a resource tonnage chart in which we have resource and reserve tonnage on the bottom and a resource reserve grade on the y-axis. And if you look specifically at the green triangles, those are the projects that come from South Africa. And what we see here is that, pretty much all of them are the highest grade that we have. And so what was going to take to compete with those projects, for these projects down here to compete with those up here? So we're going to look at, quickly run through 4 different, ways that we can potentially increase our supply, the diversity of our supply. The first one is a bullish market. So basically prices increase. And so on the bottom, what we have is that similar tonnage grade chart, but I've split it up into 2 different costs, or 2 different platinum prices. This was the 2023 price, of roughly $1,000 per ounce. And then if we look at the costs over, say, the last 30 years, prices were at their highest around 2010. And this if you convert for inflation, this gets you roughly $2,600 per ounce. So if in addition to just having that grade and tonnage, what we also have here is the color indices is the net present value. And so similar thing, if what we're seeing here is that blue is positive net present value, orange is negative. And the mines that we're mostly going to be concerned with are in this outline box. And those are the ones we're trying to get that, that they're non-South African mining projects. And so using the 23 price, none of these projects are going to be economically competitive. Then if we use this when prices were at their highest of like $2,600, still really, even with these high prices, these mines cannot move forward. They can't, but in essentially almost all the South African mines can. And so therefore that would, if these all mines were able to come forward, production would increase, price would diminish. What happens if we are figured out some way of reducing our costs, either through, we change our energy source, or somehow the reagents become cheaper in the way we're processing it. So we're looking at, what were the same kind of charts here, and what we go from no change using the $1,000 price, we reduce our costs by 20%. Nope, none of these projects are able to move forward. 50%. Nope. Say we somehow come up with a way of reducing OPEX by 50% and CAPEX by 20%. Still nothing. These projects we're still going to be have to sit there. What happens if we have some kind of technology or methodology improvement, and we increase our recovery rates, or we increase our recovery rates and reduce costs at the same time? And so if we increase our recovery rates, what I did is just say everything is going to be at, all these recovery rates are going to be 100%. We're going to recover all of it. Still, these projects cannot move forward. And then if we at 100% recovery rate, and we're more efficiency and reduce our costs, still nothing. It's only when we look at the byproduct production do we actually see some kind of change. And people familiar with the platinum group metal industry will know that these platinum projects are not just kind of produced in a void. And things, other commodities such as palladium, osmium, nickel, cobalt, and gold are all recovered from these operations. And so if we were to sum up the potential production of all the other commodities that can be produced as a byproduct, and the revenue that would be generated from these byproducts, only then do we start to see some projects outside of South Africa start to move, could eventually be economically cost competitive and be feasible. Yes, there'll be more. These projects are going to be more expensive, and that was taken into consideration in estimating the cost by the addition of all these other processing flow sheets for producing all these byproducts. But even when those additional costs are included, they're still going to be they're potentially feasible and can advance towards the production stage, and that byproduct production is going to be the way in which it can be achieved. And so, just, a conclusion for the various things that I talked about today. First is that, so within the USGS, we have put together, two mining cost models in which people can use and integrate within their own work to estimate costs for 28 mineral commodities. And this can just be done, like I said, just using simple mining parameters. And then using the rare earth mining cost model, we can estimate future supply in which, and then develop, an ex-China supply production futures. And we looked at copper, and that we see is that there are enough projects within the pipeline that we can meet these demand scenarios. This doesn't take in consideration such as permitting and things like that, and this is only just due to economics. But we do know of the projects, and there is enough potential production there, enough supply around in the ground. And then lastly, it's going to be difficult to diversify our platinum supplies, but if we integrate byproduct production, that'll aid in the cost competitiveness, for these projects that lack the grade in comparison to those from high grade deposits. And with that, I will take your questions.
Awesome job. I really appreciate it, Tim. Great information. You can go back to your question slide if you want. I just wanted to address one question in the chat that this will be recorded and available in about a week's time on YouTube. So somebody asked about that. But with that, Tim, I'll let you take it to the top of the questions list and just kind of summarize and read from there. And we got quite a few in the chat, so take it away.
Do you have coverage? So, okay, sorry. Do you have coverage concerns for rare earth mines? Are you able to estimate the entire Chinese production on a mine by mine basis? No, we are not using any Chinese operations to develop the model. This was all done using projects outside of China. I think that's what the question is asking. But for the Chinese operations that we did use for the modeling, we did have some information about the potential product, about the amount of that may be produced from those operations, or it was done by calculating production from the knowledge of the resource and reserve size. Let's see. Do you have a prediction on the greatest shortfall in 5 years? I don't know what this one is referring to. I think I'm sorry. If anyone has any questions, and you can email me, my contact is here, because I'm not sure what that one is trying to ask me. Does your regressions consider time variance events or policy impact? No, it does not. They're all using all the time. Times we're using 2024. And so we do not account for that time. Everything was brought up to for inflation for 2024, and it is not taking into effect of various policies or things like that. That's not included within the feasibility studies or the S&P data. I wonder if you have introduced a country risk factor. No, a country risk factor was not included into that, but that has been something I have been considering. I would like to consider, but no, this was just determined based upon what are the costs of that, or what are the economics within an individual project. And then, are you normalizing the return rate for all jurisdictions? Yeah, good question. Am I normalizing the return rate for all jurisdictions to establish the net present value? Yes, I am. I'm just using, I think for most of these, I believe I use a net present value of around 8 to do that. But again, so I think within the dashboard, you can adjust you can adjust the return rate, and that'll automatically update your net present value for that. Are there any U.S. mining projects, including startups, that you think will make a difference? Ooh, in the next 5 to 7 years. Oh, I think that question is probably above my pay grade that I think I should answer, especially as a USGS person. So, I like the question, but I'm not going to touch it. Sorry. If copper is considered a byproduct, how do you account for its dependence on other elements, such as nickel and zinc? Okay. In your study, are the prices of nickel and zinc assumed to remain fixed? Remain fixed when the price of copper changes. So similarly, I do not adjust the price. The price is the same over the life of the mining operation. And so then I think so the nickel and the zinc will be as well. If you want to integrate a more complex scenario in which you do bring in whatever prices do vary over time, yeah, I mean, it'd be much more realistic than what I provided. Really, what I wanted to show is just how the model can be used and with the different questions that can be answered using it. But no, that would be something that would be really interesting to incorporate is, the price change, throughout time. And so, will these projects need to go through, if all of a sudden, if the price is high and the project is operating, and then what happens if the price, dips down, and for how many years, maybe for several years, you can integrate that and with, placing a project under care and maintenance, something like that. So mine are just simple equations, and so that you can integrate within your own model. Yes. So will the presentation be available? Yes, in a week. Is temporal impact of extraction costs due to the decline of ore grade with time be considered? No, that was not considered. We did not deal with the decline in ore grades. What did you find to be the greatest cost in refining reagents, consumables, electricity? For the rare, I have it specifically for the rare earths, and the highest operating cost was the reagent cost. And so for the rare earth model, for the scenario that I showed you, all those were modeled as producing oxides. So it's going all the way. So none of them were just doing, not one of them was going to produce a concentrate, and then another one that was going to produce a MRAC or something like that. No, all of them were modeled the same way, is basically that they're all going to produce an oxide. And so from that, the reagent cost was the highest expense. Let's see, a good proxy for country risk factors is the IH. Okay. No, I do have a coal mining project cost model. No, Evan, I do not, sadly. But the information is on S&P for it to be done. I thought about including it, but since we do not follow the coal as well, we're just primarily sticking to the metal commodities. Let's see. How do you deal with geological uncertainty, as I assume such a large data set of projects will have the various different stages of exploration, quality, and stage? So how do I deal with geologic uncertainty? So for this commodity specific, for the rare earths, I was able to go down into the variation of deposit type, and primarily looking. I think we primarily looked at the difference between carbonatites and alkaline deposits. And it really didn't see too much of a difference. And I was actually quite surprised that the geology didn't really have a great influence on the cost there. I wasn't able to do it for the multivariate as well, but it is included on that non-commodity specific regressions where we go down and we look at the if it's a porphyry deposit or if it is a pegmatite or something of that nature. And so it's kind of a roundabout way we do get to that question. But if you really want to look at and study the difference, it is within the rare earth itself. The rare earth project, we do look at the effect of geology on the costs. Are you modeling both the mining and the refining of the ores? So yes, we are. So for the rare earths, it does look at there's regressions for open pit and underground mines, but then there's also for I said the three different kind of processing flow sheets. And then for the multivariate work, I take it based upon four different categories. But they're all included. So the mine and the refining are included at the same. But it's done. It's like, so if you just want to say like this is a mine that's going to produce a concentrate, you can look at that. Or if this is a mine that's going to produce a door, or that's kind of like or something that's going to produce some kind of anode, something of that nature, you can mine that as well. So really, if you want to adjust, you can adjust the mine type, and then you can adjust that broad category that I had for processing. Let's see. A good intergovernmental recommendation for this project is to allow mining projects to fully depreciate assets and discount capital gains after 10 years, much like ounce. I don't know. Okay, I'm not sure what this one is telling me. I don't know if that's fully I'm a geologist. I'm not much of an economist, so this is a bit above me. And so see, for the newly discovered lithium deposits by USGS, are you planning to do a cost analysis? I see. So for those I wonder if that's for the undiscovered deposit. So I only do it for if it's the ones within the Appalachians. If you're referring to that publication, if a reserve or a resource of reserve size is provided, it potentially could be done. There has to be a little bit of additional work that needs to go into it, but the equations can be integrated for that kind of work, as well as looking for, it can be done for looking at undiscovered deposits, which USGS also does. I do not have plans to do it right now, but that doesn't mean it won't come out in the future. But if you want to go right ahead and do it, go right ahead, have fun. Then I think I got through everything. I think I got through all the questions. Whew.
Awesome job. That was great questions from the audience today. I really appreciate that. Tim has his email on the screen. Like you said, please reach out to him if you have questions, look at the paper. And with that, we can round out our day. And so Tim, if you'd go to that last slide for me, please. Thank you. So all of you in the audience, thank you so much for attending. As a reminder, we will have this presentation available in about a week's time on our YouTube channel, Critical Materials Innovation Hub. And also you can find it at ames.gov or ameslab.gov/CMI. But if you're looking for more, please join us next time on June 23rd when Hongwei Jin presents How to to conduct techno-economic analysis and life cycle assessment. So for some of you who maybe are more interested in those economic aspects of it, this might be a great talk for you to follow up with. But with that, thank you so much all for your time, and thank you, Tim, and I hope you have a great rest of your day.